Our first speaker this morning is James Ladyman from Bristol, who is going to be giving us an argument for retrocausality. Welcome, James.
Thank you very much. Well, thanks for coming. We waited for you. So this is the plan. What I want to do is try to get clear about why we have the intuition that there's something retrocausal about weak values, if we have that intuition. I think lots of people do. So it's in the spirit of getting a clear argument on the table that you can then talk about whether you think it's a good one and which premises you might reject and so on. So I'll give a very brief review. I think lots of people here aren't just familiar with this stuff, but actually invented it. So they can kind of go to sleep during that bit, but some people won't know it all. So I'll quickly give a review of the physics, and then I'll talk about what I think is the probabilistic structure of a particular kind of weak values experiment, and then give the argument, and then talk about counter examples and objections that I got when I gave this paper at the Sigma Club in London, and then briefly conclude. Before I start, I should say that this talk is based on a paper I wrote with a former student, Katie Robertson. She's now at Oxford. And I'm very grateful to Sandhu, though he is not to be held responsible for anything I get wrong. But he's introduced me to this topic and given me a lot of help with it, so thanks to him. Okay, well, weak values can only be measured by weak measurements, but not all weak measurements are of weak values. That's the headline there. A weak measurement, basically the idea is turn down the strength of the interaction between the apparatus and the system so that the measurement gives you information about the system with a wide margin of error, but correspondingly you don't collapse the system or disturb the system or change the probabilities for later measurements. That's the basic philosophical point, I think, about weak measurements. So for all practical purposes, the system is regarded as undisturbed by a weak measurement. It's treated as if it's in the same state. The probabilities for later strong measurements are unchanged. Imagine that the wave function of the measuring device pointer has a Gaussian distribution. In weak measurement, the idea is that the width of that Gaussian is wider than you'd want it to be for a completely precise strong measurement. And that width, that uncertainty in the pointer position, is what allows the measurement to not change the state of the system. The smaller the uncertainty, so this QD is the position of the pointer. That's a pointer position observable. And there's this trade-off. The smaller the uncertainty in that position of the pointer, the smaller the uncertainty in the observable that we're measuring. So in strong measurement, the width of the Gaussian is narrow, the uncertainty in the pointer position is small. In weak measurement, the pointer position spread is typically larger than the spread of the eigenvalues. So if you're measuring on a single system, then weak measurement can be practically useless. It can tell you practically nothing. And the relevant fact that I'm going to use here, that's going to be important for what follows, is that you can weakly measure n spins with a minimum error of plus or minus root n. Then you see immediately that if n is small, this is completely useless. If n is very large, then this can be extremely informative. And you could say, well, I can measure it as accurately as I want if I make n big enough. So I'm going to talk about the case as for convenience where n is 100 and root n is obviously 10. Now, the next ingredient that we need is PostSelection. So people were talking about this yesterday, the idea, ordinarily in quantum mechanics we think in terms of a Hamiltonian formulation with initial conditions of state preparation, but PostSelection is just the idea that we have boundary conditions. We have a condition about the end of the experimental setup as well as about the beginning. And we can talk about a pre- and post-selected ensemble. What we mean by that is, well, first we will prepare the system in some state by performing some measurement, putting it in some known state. Let's say in the case we're going to talk about, the system's going to be in the state up in spin x direction. And we can also then imagine a sequence of measurements and at the end some final measurement. And we can have a very big ensemble, and then we can take the sub-ensemble that satisfies some condition on the final measurement. And that's what post-selection is. So we have some final measurement and we only consider the sub-ensemble that satisfies that condition. So you talk about a PPS ensemble, pre- and post-selected ensemble. Now, post-selection changes the conditional probabilities for intermediate measurements. And there's nothing mysterious about that in general. In a classical setting, post-selection would change our probabilities. So, example I like to give, suppose you've got a longitudinal study of school children. How do they do it at GCSE? How do they do at A level? How do they do at university? You pre-select the ones who, get some grade point average when they're 12. And then you consider the probability that they do well at A level. Let's say get 3 A stars. Well, obviously, if you post-select the sub-ensemble that get a first at university, it changes the probability of getting 3 stars. Right? And there's nothing mysterious about that at all. So in general, post-selection is perfectly well defined on any probabilistic, any domain of events about which we have probabilities. It's just a matter of conditionalizing on something. The interesting thing is that in quantum mechanics, in classical situation, you could always imagine replacing post-selection by a more careful pre-selection. Or you might think, if you knew all the information about the system, then the post-selection wouldn't tell you anything. So those kids that did well at GCSE and then got A stars and then went on to get a first, maybe if you knew enough about them, you wouldn't need the information that they got a first at university. You could predict their A stars. In the quantum mechanical domain, because of indeterminism, basically, I think, there's always extra information to be had by post-selecting. So if you think about just fix your intuitions, to think about in the very simplest case, suppose you have a system with no Hamiltonian acting and you pre-select it's up in spin x, and you're imagining that the final measurement is up in the z direction. That's what you post-select for. Clearly that changes the probability of an intermediate measurement in the z direction, just trivially, right? You know if it was a projected measurement, there's no Hamiltonian, if it ended up being up, and had you measured it in the z direction in between, it would have been up. So post-selection changes the transition probabilities for intermediate measurements. So what we're going to do now is put together weak measurement and post-selection. And then what we'll talk about now is having a pre-selection, having an intermediary measurement that's weak rather than strong, and having a post-selection so that we can select a sub-ensemble and look at how that sub-ensemble behaves with that intermediary, under that intermediary weak measurement. So forgive me if this is really teaching you things that you all know really well, but I suppose we can just think about it as trying to get the core kind of philosophical structure of it completely clear. Okay, I've said all that. Okay, so now we get to weak values. What are weak values? Well, the weak value is something analogous to an expectation value, not exactly. I don't want to say really what the weak value is. This is the definition of it. So it's defined for a pre- and post-selected sub-ensemble, or perhaps it might just be a single system. And the real part of this is what we can talk about measuring as the weak value. It will be an outcome of a weak measurement. So let me get on to an example. So basically the idea is this, okay? You have a strong measurement. You know the initial state of a big ensemble of systems. You make some weak measurement. You then make a post-selection based on the result of a final strong measurement. When you look back at the sub-ensemble, that has been post-selected for, the results of that are distributed around what's called the weak value, the results of the intermediary weak measurement on the sub-ensemble. Okay. So the case I'm going to talk about, we're going to have spin up in the x direction, is upstate preparation. So initially we measure spin in the x direction, we throw away everything that isn't up. Our final measurement is going to be spin in the z direction, and we're going to throw away everything that isn't up for that too. And our intermediary measurement is going to be spin 45 degrees between so spin in between x and z. Okay. So the expectation value for the weak measurement will be 1 over root 2 for one spin. For n spins, the expectation value is 1 over root 2 times n for the weak measurement as a whole. But when we look at the post-selected sub-ensemble, that expectation value shifts up to be outside the eigenvalue range, outside the range of normal eigenvalues for that intermediary measurement. And this is what people talk about, that you could make this weak value as big as you like. You have some overlap in the initial state and the final state, and by choosing things, you can arrange things so that you can make the numerator very big and make the weak value be enormous. So people talk about measuring spin 100 on a spin half system, getting a result of spin 100. But you will have a very, very small proportionally sub-ensemble in that case. Let me maybe move on and things will become clearer. So I want to talk about 100 spins, because it's just going to make things easy. And I'm not being careful, I should really talk about spin half, 100 spin half, but let's just not worry about that, okay? So it's 100 spins. And we could suppose that we had 100 single particles, or managed to make a spin 100 system. So they're all, everything's up to start with in the x direction. We make this weak measurement of spin 45 degrees between x and z. We make a final spin z measurement. The expectation value of the weak measurement is 1 over root 2 times 100, as already said. The result is a Gaussian centered on that value with a width of 20, because the uncertainty is plus or minus root n is 100. But when we post-select on the result all up in z, and look at the results of the weak measurement for that sub-ensemble, we find a Gaussian with the same width, centered on the weak value, which is way up outside the eigenvalue range. And the reason that I picked this example is just so we can make you could have a weak value where that Gaussian was overlapping with the rest of your distribution. What we want is a nice case where the weak value is way up, way away, and more than the width of the Gaussian away from the rest of the distribution. So we've got an initial distribution here. I don't have a board, unfortunately. And then the weak value is way up there, so that that main part of that Gaussian does not overlap with the Gaussian around the weak value. And the reason I want that is because I want to talk about, so here's a nice picture. Yeah, so that bit where I was doing this is this. So this is from the paper by Aharonov, Pesca and Tollefson in Physics Today, which is a beautiful, accessible, short introduction overview of weak values. And the idea is, well, we've got this big ensemble. When we post-select, we're throwing away masses and masses of experimental results, because the probability of this spin n system giving all up in z at the end is very, very low. We have to throw away a huge proportion of the results. So the probability is 1 over 2 to the n of getting all up at the end. If they were all up in x, we've got a probability of a half of getting up in z. There's n of them. So obviously n's 100, 1 over 2 to the n is a very small number, so we're throwing away a very, very big proportion of the results. So that's why they're zooming in so much here. And we're up in the tail of the distribution, the tail of the Gaussian distribution of the weak measurement result. But when we throw away all of the members of the ensemble that don't pass the post-selection test, we find this little Gaussian peaked around the weak value. That's what's going on. Okay, so I want to consider the experimental results in the following way. Now, it's kind of misleading if you talk about in advance, if you say, oh, well, what I'm going to be interested in is what's the probability of passing the post-selection given that I got the weak value? What's the probability of getting the weak value given that I passed the post-selection? But you can say, well, what do you mean the probability of observing the weak value? That doesn't make any sense. It's only a weak value if it's defined on the post-selected ensemble, right? So to avoid that problem, I just want to talk about the experimental results now, and I'm going to call result R getting a result. I say that we satisfy the, we say it's a result, it counts as a result of the result R if we get a result that's within 10, within the width of the Gaussian of the weak value. So it doesn't matter, it's not a weak value, it's just a result, right? We've got a graph and we can look at it and ask the question. For a particular run of the experiment, was the value observed within 10 of the weak value? Okay? So I'm going to call that R. And I'm going to call the result of the final measurement being plus 100, F. So R for result and F for final. I don't know why these letters have stuck, and I've confused myself if I change them now. So look, what I want to do now is just talk about the probabilistic structure of this and see if I can convince you that there's some reason to think there's retrocausality, and then we can talk about it in discussion. So the important thing for my purpose is not going to be the details of the physics so much, but just have I got this probabilistic structure right and what does it tell us? So R and F are both very unlikely. Okay, we saw already that F is extremely unlikely. Well, so is R. If you go back to that picture, it's way out in the tail of this original Gaussian for the weak measurement result. So I write that. Since the measurement is weak, then by hypothesis, not by hypothesis, but by what is said about weak measurements, that for all practical purposes they don't change the probability distribution for later measurements, then we should say that the conditional probability of the final result, given that we observe that there's this value near the weak value, should be the same as the unconditional probability of the final result. So what that's telling us is that if I observe one of these pathological outlying cases of a weak measurement, it doesn't make me think that the post-selected result is any more likely than I thought it was anyway. Okay, I learn nothing about the probability of the later post-selection result by observing that pathological weak value. And that's why I can just say that it's just an error. I mean, that's one way of looking at it. In the beautiful book, Aharonov and Rawlik talk about this as a game of errors. I think that's a phrase from their book. But the probability, and this is the important bit, the probability of the weak value, the result near the weak value, given F, is much, much bigger than the probability of that result unconditionally on anything. In fact, it's very nearly 1. For all practical purposes, it's 1. Right? Because we have a Gaussian centered on that. When we take the sub-ensemble that passes the post-selection test, we have a Gaussian centered on the weak value. So these are the relevant facts. Knowing that the system passes the post-selection doesn't just change the probability of getting something like the weak value, it changes it as much as it possibly could. It goes from nearly no probability to near certainty. And that's the thing that you see and you think, wow, there's something maybe retrocausal about this. So I'd say that if you didn't know anything about the time order of the events here, you'd think that there was a causal relation between F and R. You know, if you're just open-minded and someone showed you this structure. Now, of course, that's a defeasible thing to think. You know, probabilistic structures can be very complicated. Philosophers all learn about Simpsons paradox. You know, just because something raises the probability of something doesn't mean it's a cause. Just because something lowers the probability of something doesn't mean it's not a cause. But ceteris paribus, prima facie, you've got a probabilistic structure like that, you'd think that F caused R. Moreover, of course, this is all in the context of carefully shielded quantum experiment where there aren't lots of other causal factors supposedly in the mix, right? Things that give rise to Simpsons paradox aren't supposed to be going on. We're not talking about, you know, trying to see whether, you know, having boiled eggs correlates with heart disease or something. Sorry, yeah?
I'm sorry to interrupt, but do I understand you to be saying that there is no disturbance when you measure a pointer in any particular, when you are doing what you call a weak measurement, and you have a system that is correlating with the pointer, that when you measure the pointer, you're calling that no disturbance? Because that changes the system from an improper mixed state into a pure state, however tiny that influence may be. I just kind of have to...
Okay, let's come back to that in discussion. I mean, I think what we're saying is no influence for all practical purposes. The quantum state is left unchanged. Now...
But it is changed. It's really changed. I'll let you go, but...
Okay, let's come back to that in discussion, because that's one way to go. Is that, I mean, I'm going to raise the possibility that'll be an option for you, given the way I'm going to carve things up. Okay, let me go on, because I'm... Okay, so you have to indulge me here, but it's early in the morning, so we can warm our brains up by looking at this little argument, because a referee for an esteemed journal said that this probabilistic structure that I just gave you is inconsistent and violates Bayes' theorem. So they said that because they said, well, look, that's Bayes' theorem there, so we know that's true. And we know that P of R given F is very, that shouldn't be equal, sorry, that should have been a nearly 1. So this is just PF over PR. And then they said, this referee was really rude about the paper. I don't know if the referee's here. But we got some things wrong. And you know, we did get some things wrong. But not this. So then they said, but look, P of F given R is very nearly PF, right? So if I divide through over here, then that just tells me that PR is equal to 1. Sorry, so put PR over here, divide through by PF given R. PF over PF given R, well, they're very nearly equal, so that's very nearly 1. So PR is very nearly 1, but PR isn't very nearly 1. The whole point about these weak value results is they're very rare. So this probabilistic structure, so the referee said this isn't retrocausality, in fact it violates the probability calculus. So where's the mistake? This isn't true, right? If you have big numbers and they're very nearly the same, then their ratio is very nearly 1. If you have incy-bincy tiny numbers and they're very nearly the same because they're both very nearly 0, so from a probabilistic point of view, you might say these two numbers are both effectively 0, their ratio can be arbitrarily big, obviously. 1 over 10 to the 15 divided by 1 over 10 to the 18. Well, that isn't anything close to 1, but those numbers are, for all practical purposes, the same number, right? So that's the mistake there. These things don't violate the probability calculus. So it's a kind of, what's being got at really is it's a kind of context dependence of what you mean to say approximately equal to. Anyway, so if you're worried about that, don't worry about it. They don't violate, the probabilistic structure doesn't violate Bayes' theorem. So I'm going to stick to the probabilistic structure and try to look at the options. So what are the possibilities? Well, accidental correlation, common cause, R causes F or F causes R. Now, of course, as I was saying before, if we were in some other domain, there might be lots of other possibilities, confounding factors, all sorts of complicated causal structure. But we're assuming here that this is a system that we're keeping isolated from the environment. We know what we're doing to it. There's no Hamiltonian. So these are the only possibilities. There aren't any other causal factors involved. Well, I say that accidental correlation is ruled out by the scientific method. I mean, that's a bit glib, but roughly speaking, I think that's right. When we see persistent, robust, projectable correlations in the world, we assume there's a reason for them. We think of them as evidence of causal or law-like structure. Now, we could say, oh, well, it's just a coincidence, right? But so I was talking to Jeff last night, and he reminded me of this very important point about weak values, which is that they can be detected by physically different modalities, right? You don't have to use the same technique to observe. So if you have a weak value of a particle in a box and it's a charged particle, then you can detect that by a charged massive particle. Then in principle, you could weakly measure it by interacting electromagnetically with it, or you could weakly measure it by interacting gravitationally with it. And either way, the weak value is supposed to be there. So if you put weak values down to errors, well, it starts to become a bit conspiratorial when these errors in logically independent methods of measurement have to coincide with each other. So I won't say anything more about that. I just think, no. Now, is there a common cause? Well, assuming quantum mechanics complete, then no. Of course, at Bohmian, they're not going to have a problem. They're going to say, oh, right, this is just more evidence that really the particle knew what it was going to do all along. It had some hidden variable which was determining what it was going to do in the weak measurement and determining what it was going to do in the final strong measurement. So we don't have to worry about this later strong measurement causing the weak measurement result, because it was all proceeding according to plan anyway. But that's always an option. You could always be a Bohmian. Now, you could say, well, the causal structure goes this way round, right? The weak measurement result causes the final post-selection event. Well, it doesn't raise the chance of it more than negligibly. And also, I think, if this is the right option to take, then some story has to be told about that, because the standard story doesn't say anything about that. There's had to be some story about what's going on in this quantum mechanical system, such that this weak measurement result is then changing it in such a way as to bring about the later post-selection result. And of course, it's not changing all of them. The vast majority of the systems that have a result near the weak value don't later give you the post-selected result you're selecting for. So the last option is F causes R. Well, I don't want to say actually causes. I'll come back to this at the very end. I just want to talk about some kind of causal dependence, right? Being neutral about what it takes to be a cause. But what I'm really trying to say is there's a law-like structure in the probabilities that's indicative of causal relatedness of these events. We then have a choice about what kind of causal relatedness we think that is, and those are our options. Now, before I finish, I'm going to spend most of the time on discussion, but I'll just give you some counter examples and objections. So Simon Saunders' response to me giving this paper in London was to say, oh, but look, the probability of me being born, that's nearly zero. The probability of my parents meeting, that's nearly zero. But the probability of my parents meeting, given that I'm born, is very nearly 1. Isn't that like your weak values case, right? But no retrocausality. Right, my response to that, well, I'll come back to my response to that. I'm going to give you another version of it. Probability of living to 1,000 is very small. Probability of living to 100 is very small, but the probability of living to 100, given that you live to 1,000, is very nearly 1, right? Well, is 1. In both those cases, it's 1, and then this one is not quite 1. Probability of being a member of the cabinet is tiny. Probability of going to an elite public school is tiny. The probability of going to an elite public school, given that you're a member of the cabinet, is very close to 1. right? So, and at the moment, that's especially true, right? And it's all one particular elite public school. So, the point about that is, you know, in each of these cases, the thing in the future is the thing you're conditionalizing on, but it's raising the probability for something in the past. Well, my response to all of these is just to say, yeah, so the objection is there's no retrocausality, but don't they have the same probabilistic structure that you were just talking about, so you don't have any retrocausality either. My response to all of those is to say, yeah, but in every one of those cases, the early event is definitely a cause of the later event, right? And moreover, in every one of these in these cases, the probability of the later event is significantly raised by conditionalizing on the earlier one, right? Simon's birth is still unlikely, but much more likely given that his parents met. Being a member of the cabinet is much more likely given that you went to public school than the unconditional probability of being a member of the cabinet. Living to 1,000 is much more likely given that you live to 100. So, well, we don't have that in this case, right? We don't have the reciprocal probability raising. And moreover, these objections all concede that there's a causal relation between these events, right? They're all examples where there's a causal structure. And I think they're disanalogous, and therefore we don't get the same reason to believe that from the probabilities that the causal structure is one where we want to say there's a causal dependence of the past on the future. I won't say past and future, I will say of the earlier on the later. Good, and then this objection from, sorry that Adam's not here, Adam gave me this objection as well. He pointed out that, look, these ratios just have to be the same by Bayes' theorem, right? And so he was sort of like, well, if you think that this is the likelihood ratio, this tells you how much you should think that one thing is a cause of the other, and these numbers are the same, so you couldn't have any reason to believe that the weak value is caused by the post-selection result than the other way around. And I think, well, very quickly, I mean, people sort of see what they think about this, but I think this is a better measure of how much something tells you that something's going to happen. This is a better measure of a causal relation in the absolute difference between the probabilities rather than the ratio. Because, well, we've just seen that the ratio can be the same, even though in one case the difference in the absolute values is very nearly 1. In the other case, it's it tells you virtually nothing. And the reason why these two things can be true at the same time as that thing being true is because PR is actually much, much bigger than PF, right? Even when you zoomed in on the tail of the Gaussian, there's lots of things there that you throw away. Good, so what kind of retrocausality? Well, let's just note, first of all, you can't signal with this. Causal dependence only apparent for the ensemble, not for individual measurement results. I don't know how significant I think that is. Of course, we're talking about time-like related events here. And I think I've got on the table the argument I wanted to give and let people see what they think about it. As I say, I don't particularly have a dog in the fight here or whatever. I'm not sort of true believer in retrocausality. But when I first heard about weak values, I had this feeling that there's something retrocausal about it. And what I've tried to do is make some plausible reasoning behind that intuition explicit, so that we can interrogate it and see that that's whether or not that's what we should believe. Okay, thanks very much.